You know, every now and then, a paper comes out that doesn't just tweak an existing idea, but hints at a fundamental shift in how we build AI. And today, we're diving into one of those. We're looking at a brand new architecture called Retentive Network, or RetNet for short. And its creators? Well, they're positioning it as a potential successor to the reigning king of AI, the Transformer. So let's see if this challenger actually has what it takes. The authors of the RetNet paper kick things off with this quote from Arthur C. Clarke, and honestly, it sets the stage perfectly. They're not just trying to build a slightly better transformer. No, they're aiming to solve what has long been considered an impossible problem in how these models are designed.
So what is this huge problem we're talking about? Well, it all boils down to cost and efficiency. See, transformers are amazing for training. You can just throw a ton of data and a ton of GPUs at them all in parallel and it works. But once they're trained, actually running them, what we call inference, is incredibly slow and super expensive. RetNet's big promise, its whole reason for being, is to give us the best of both worlds. Keep that fast parallel training, but make inference ridiculously cheap. The paper frames this whole challenge in a really cool way, calling it the impossible triangle, or the AI architecture trilemma. It's a concept that really gets to the heart of the tough trade-offs that AI developers have been forced to make for years.
So here are the three corners of that triangle. First, you want fast parallel training. That's a must. Second, you want cheap, efficient inference. And third, of course, you need the model to actually be powerful and perform well. Now, for the longest time, the rule was you could only pick two. You could have a model that's fast to train and performs well, but it'd be expensive to run. That's a transformer. Or it could be cheap to run and perform well, but it would be painfully slow to train, like an old-school RNN. Getting all three at the same time? That's been the holy grail. And this is where RetNet storms onto the scene. The creators, they do not mince words. Right there in the abstract of their paper, they make this incredibly bold claim. RetNet has what it takes to be a strong successor to the Transformer. So the big question is, how on earth do they claim to have solved this impossible triangle?
And that question right there brings us to the core innovation. I mean, how can a single model be parallel for training, but then somehow be sequential for inference? On the surface, it just sounds contradictory, right? Well, the answer lies in a truly clever design that lets the exact same model operate in fundamentally different ways.
Okay, so when this paper dropped, one of the first things people started asking online, in places like the Hugging Face community, was exactly this. Wait, why are there three different modes? Why three representations? It sounds complicated, I get it, but this is actually the secret to its power. Let's break it down.
These are the three faces of RetNet, but they're really just different ways of calculating the same result. For training, it uses a parallel mode. It acts just like a transformer, crunching data at incredible speeds. But then, for inference, it flips a switch to a recurrent mode. This mode operates one token at a time, making it incredibly cheap and fast. And here's the magic trick. It's the exact same model, with the same weights. You just swap out the computation style. It's brilliant. There's even a third chunk-wise mode, which is a kind of hybrid for handling super long sequences. Okay. A clever design is one thing, that's great, but the proof is always in the pudding, right? The paper gives us a direct head-to-head comparison. So how does RetNet actually stack up against the mighty Transformer when we look at the hard numbers? Let's check out the data. Now get ready for this, because the difference here is just staggering. We're looking at a 7 billion parameter model with a pretty long context of 8,000 tokens. RetNet's throughput, so how many words it can process per second, is over 8 times higher. 8 times. It uses 70% less GPU memory and has way lower latency. Look, this isn't some small incremental improvement. This is a massive leap forward in efficiency. And this chart right here, this shows you exactly why it's so efficient with memory. With the Transformer, a huge chunk of your GPU memory gets eaten up by something called the KV cache, which has to store all the context from the text that came before. RetNet's recurrent mode just gets rid of that completely. The result? A massive 97% of the memory is just from the model weights themselves, with almost zero inference overhead. It's crazy efficient. But what about training, right? It can't be good at everything. Well, it turns out RetNet is not just an inference champion. It's way more memory efficient and has much higher throughput than a standard transformer. But here's the real kicker. It's even competitive with, and in some cases a little better than, a highly optimized transformer using flash attention. And it does all that with just standard PyTorch code. No special tricks needed.
All right, so we've checked off 2 corners of our impossible triangle. We've got the parallel training, and we've got the super low-cost inference. But now we come to the billion-dollar question. What about that third corner? What about performance? Because a faster, cheaper model is totally useless if it's not as smart.
So this chart measures something called perplexity. It's a common way to measure language model quality, and lower is better. And it tells a really fascinating story. At the smaller model sizes, the transformer has a tiny little edge, but watch what happens as the models get bigger. RetNet catches up and then it pulls ahead. By the time you get to the 6.7 billion parameter size, RetNet is clearly outperforming the transformer. This suggests its architecture just scales better.
And hey, this isn't just some theoretical advantage on a perplexity score. When you test it on actual downstream tasks that measure things like reasoning and common sense, tasks like HeliSwag and COPA, the 6.7 billion RetNet model consistently beats its transformer twin. The average accuracy is more than 3 points higher, and in the world of these benchmarks, that's a really significant win.
So, let's look at the final scorecard. Training parallelization? Yep, both get a check. Performance? Both are really strong, but now look at the differences that matter. Inference cost for a transformer grows with the length of the text. For RetNet, it's constant, O of 1. Transformer memory usage gets quadratically worse. RetNet's is just linear. It seems that on all 3 fronts of that impossible triangle, RetNet actually delivers.
So the next logical question is, when can we all get our hands on this thing? Well, one of the paper's authors, Yutao Sun, actually commented directly to the community. He said that releasing a high-quality pre-trained model is definitely in their plan, and when they do, a full Hugging Face integration will be ready to go. That is a fantastic sign that they want to get this tech out there for everyone to use.
And that brings us to our final thought here. The numbers, the charts, they're all super impressive. But let's just step back for a second. What does all this actually mean? If AI models suddenly become 8 times faster and 70% cheaper to run, if you can run these powerful models on cheaper hardware, maybe even on your phone, what new things become possible? What can we build when the single biggest bottleneck to deploying AI at scale is suddenly dramatically removed? That is the truly exciting question that RetNet leaves us with.